So in the previous class, we were learning about the molecular orbitals of the hydrogen molecular ion, like H2 plus. H2 plus in the molecular orbitals ion molecular orbitals H2 plus ion in the molecular orbitals in the class. So we got the expression for two molecular ions. The one molecular ion was Psi plus, and the expression for Psi plus is 1 divided by root of 2 into 1 plus s into 1 as a plus 1 as b. Okay, and there was another molecular orbital, that is psi minus, and the expression for psi minus is 1 divided by root of 2 into 1 minus s into 1 as a minus 1 as b. Okay, and here 1 divided by root of 2 into 1 plus s and 1 divided by root of 2 into 1 minus s. These are actually the normalization factors. Okay, so this one corresponds to the energy E plus, and this one corresponds to the energy E minus. With the E plus energy profile, it corresponds to a minimum, and if the electron is occupying the Psi plus molecular orbital, then it will be following the energy profile of E plus, which has a minimum at a certain internuclear distance of 1.32 angstrom. It has a minimum means that its energy corresponding to that minimum is less than that of the individual hydrogen molecular orbital. Right? So E plus energy state hydrogen molecular ion 1.32 angstrom internuclear distance the energy individual hydrogen molecular individual hydrogen atomic orbitals energy കുറവാണ്. അതുകൊണ്ട് അതൊരു സ്റ്റേബിൾ അറേഞ്ച്മെന്റ് ആണ് എന്ന് നമ്മൾ പറഞ്ഞല്ലേ. അതുപോലെ ഇ മൈനസിന്റെ കേസിലാണെന്നുണ്ടെങ്കിൽ ഓൾവേസ് ദ എനർജി ഓഫ് ദി ഇ മൈനസ് energy corresponding to any internuclear distance. Okay, if it is in the E minus profile, it will be greater than the energy of the atomic orbitals. Okay, so Psi plus molecular orbital electron occupy അത് E minus profile ആയിരിക്കും അതിന്റെ എനർജി ഇരിക്കുന്നത്. ആ E minus എന്ന് പറയുന്ന എനർജി ഏത് ഇന്റർന്യൂക്ലിയർ ഡിസ്റ്റൻസ് എടുത്ത് നോക്കിയാണ് അത് ഹൈഡ്രജന്റെ ഇൻഡിവിജ്വൽ അറ്റോമിക് ഓർബിറ്റൽസിന്റെ എനർജിയേക്കാൾ കൂടുതലായിരിക്കും. therefore that is going to lead in unstable system അല്ലേ. അപ്പോൾ ഇലക്ട്രോൺ എപ്പോഴും താല്പര്യപ്പെടുന്നത് Psi plus മോളിക്കുലർ ഓർബിറ്റിൽ ഇരിക്കാനായിരിക്കാം, അല്ലെങ്കിൽ Psi മൈനസിലേക്ക് പോയി കഴിഞ്ഞാൽ ഇലക്ട്രോൺ കൂടുതൽ സിസ്റ്റം കൂടുതൽ അൺസ്റ്റേബിൾ ആണ്. അതൊക്കെയാണ് നമ്മൾ കഴിഞ്ഞ ക്ലാസ്സിൽ ഡിസ്കസ് ചെയ്തുകൊണ്ടിരുന്നത്. Today we can see how the electron density is distributed along the internuclear axis. Okay, the internuclear axis electron density we calculate. First of all, we will suppose that the electron is occupying the Psi plus molecular orbital. Okay, ഇതാണ് നമ്മുടെ occupied molecular orbital. നമ്മൾ സപ്പോസ് ചെയ്തിട്ട് ആദ്യം Psi plus corresponding ആയിട്ടുള്ള electron density നമുക്ക് കണ്ടുപിടിച്ച് നോക്കാം. So the electron density corresponding to Psi plus will be obtained by the probability, that is Psi plus square. Psi plus square ആണ് Psi plus corresponding ആയിട്ടുള്ള probability എന്ന് പറയുന്നത്. So Psi plus square is equal to 1 divided by 2 into 1 plus s into 1 as a plus 1 as b the whole square, that is equal to 1 as a square plus 1 as b square plus 2 1 as a 1 as b. But 1 as a 1 as b എന്ന് പറയുന്നത് എന്താണ്? Actually it is 1 as a is the atomic orbital, 1 as atomic orbital of the hydrogen atom A. 1 as b is the hydrogen 1 as atomic orbital of hydrogen atom B. ഹൈഡ്രജൻ ആറ്റം എയും ഹൈഡ്രജൻ ആറ്റം ബി യെയും നമ്മൾ രണ്ട് ഇൻഡിവിജ്വൽ ഹൈഡ്രജൻ ആറ്റംസ് ആയിട്ട് നമ്മൾ കണക്കാക്കി കഴിഞ്ഞാൽ, ഓക്കെ, അപ്പോൾ ഹൈഡ്രജൻ ആറ്റം എയുടെ 1 as അറ്റോമിക് ഓർബിറ്റലാണ് 1 as A, ഹൈഡ്രജൻ ആറ്റം ബിയുടെ 1 as അറ്റോമിക് ഓർബിറ്റലാണ് 1 as B. ഓക്കെ, ആക്ച്വലി നമ്മുടെ H2 പ്ലസ് എന്ന് പറയുന്ന സിസ്റ്റം ഇറ്റ് ഈസ് കോൺസ്റ്റിറ്റ്യൂട്ടഡ് ബൈ an H പ്ലസ് പ്ലസ് ഹൈഡ്രജൻ ആറ്റം ആണല്ലേ. പക്ഷെ ഇതിന്റെ ഈ ന്യൂക്ലിയസിനെ H പ്ലസിന്റെ ന്യൂക്ലിയസിനെ എ എന്നും അല്ലെങ്കിൽ മറ്റേതിന്റെ ന്യൂക്ലിയസിനെ ബി എന്ന് വിളിക്കുന്നു. നമുക്ക് വേണമെങ്കിൽ തിരിച്ചും കൺസിഡർ ചെയ്യാം. ഇതാണ് എച്ച്, ഇതാണ് എച്ച് പ്ലസ്. ഇങ്ങനെ തന്നെയാലും ദർ ആർ ടു ന്യൂക്ലിയേ എ ആൻഡ് ബി. ഓക്കെ, അപ്പോൾ ഈ രണ്ട് ന്യൂക്ലിയസുകളും രണ്ട് ഹൈഡ്രജൻ ആറ്റത്തിന്റെ ന്യൂക്ലിയസ് ആണ് നമ്മൾ കൺസിഡർ ചെയ്ത് കഴിഞ്ഞാൽ, ഓക്കെ, അതിന്റെ 1 as അറ്റോമിക് ഓർബിറ്റിലാണ് ഈ 1 as എയും 1s p എന്ന് പറയുന്നത്. A എന്ന് പറയുന്നതിൻ്റെയാണ് 1s A. B എന്ന് പറയുന്ന ഹൈഡ്രജൻ ആറ്റത്തിൻ്റെയാണ് 1s B. So that we already know that. And what is the expression for 1s A? 1s A is equal to 1 divided by root pi e raised to minus RA, and 1s B is equal to 1 divided by root pi into e raised to minus RB, where RA is the distance of the electron from the nucleus A, and RB is the distance of the electron from the nucleus B. Okay, now what we are going to do is we are going to see what is the electron density between the nucleus, between the nuclei. Okay, so here is our internuclear axis. This is internuclear axis, and then we have two nuclei here, the nucleus A, and this is nucleus B. It's nucleus A, and this is nucleus B. And in between nucleus, in between these nuclei, this is a point in between the nucleus. Okay, so in between the nucleus, what is the value of this function psi plus square? That is what we are going to establish. Okay, let's examine what is the value of psi plus square in between the nucleus. In between the nucleus, this is RA. Okay, this is RA. RA, that is the distance of the electron from the nucleus A to the electron. ഈ ഇലക്ട്രോൺ എന്ന് പറയുന്നത് മിഡ് പോയിന്റിലാണ് നമ്മൾ കൺസിഡർ ചെയ്യുക. അങ്ങനെയാണെന്നുണ്ടെങ്കിൽ ഇവിടെ നിന്ന് ഇവിടെ വരെയുള്ള ഡിസ്റ്റൻസ് ആണ് RA. And if we are considering RB for the midpoint, then this is RB. So you can look at this. RA is equal to RB here, right? RA is equal to RB. So in between the nuclei, RA is equal to RB. So when RA is equal to RB, then what will happen to 1s A and 1s B? We can check. See, you suppose that RA is equal to RB. Then what is the expression for 1s B? 1s B is equal to 1 divided by root pi e raised to minus RB, where RB is equal to RA. Therefore, we can write minus RA. So 1 divided by root pi into e raised to minus RA. What is that? That is actually is 1s A. So we can write it like 1s A. So in between the nuclei, 1s A is equal to 1s B. 1s B is equal to 1s A in between the nuclei. So 1s A is equal to 1s B, and therefore psi plus square at that point, psi plus square in between the nuclei is equal to 1 divided by 2 into 1 plus s into 1s A square plus 1s B square. 1s B is equal to 1s A in between the nuclei. Therefore, we can write it like 1s A square plus 2 into 1s A, right? Because instead of 1s B, I wrote 1s A. And that is equal to, actually what is this? 1 divided by 2 into 1 plus s. It's the square of the normalization factor. Okay, so I can write it like n square also, n square, just for simplicity. Otherwise we can maintain 1 divided by 2 into 1 plus s, no problem. Or you can just write it like n square, that is a square of the normalization factor, where n is equal to 1 divided by root of 2 into 1 plus s here. Okay, so n square, since it is the normalization factor psi plus, we can write it like n plus. Okay, this is n plus represent the normalization factor of the psi plus. So n plus square into 1s A square plus 1s A square plus 2 1s A square, that is equal to 4 1s A square. 4 into 4 1s A square. So that is equal to 4 n plus square 1s A square. That is the probability density in the midpoint of A and B, right? So now we can consider, just to we go for a hypothetical situation. You suppose that the nucleus is separated at this internuclear distance itself. What is this internuclear distance that we calculated? This is around 1.32 angstrom, right? 1.32 angstrom. That is what we calculated in the previous class, right? I think we calculated the same. Yes, 1.32 angstrom. And uh, at this distance, we are keeping the hydrogen H2 plus, the nuclei of the hydrogen H2 plus. The nuclei are nuclei A and nucleus B, and both of them are kept at a distance of 1.32 angstrom. So, what is this distance? This distance from here to here is 1.32 angstrom, just like we kept it here. Okay, here we consider that bonding is there. Okay, but in the other case, bonding is there. That is why we consider the bonding molecular orbital. Psi plus is a bonding molecular orbital. Okay, or molecular orbital, or it means that it makes a molecule. That is what we consider here. It makes a molecule. These two nuclei and one electron makes a molecule, that we assumed there. And then we consider the molecular orbitals, and we examine the square of the molecular orbital in the midpoint of A and B. What we are going to consider here is that we only suppose that the two nuclei are there and one electron is also there. Okay, the electron can be either in the custody of A or it can be in the custody of B. Okay, so here the thing is that, and you just suppose that no molecular orbital is being formed. No molecular orbital is being formed. But these two nuclei are kept at the distance of 1.32 angstrom, and in between the nuclei, we are going to examine the electron density here. Okay, so here it is not going to form a molecule. So we don't need to consider the molecular orbital here. We only need to consider the atomic orbitals, right? So we need to consider the atomic orbitals, the sum of the atomic orbitals squares at this point. So the probability at this point, the midpoint, if there is no molecular orbital formation is happening, then at that case the probability is 1s a square plus 1s b square. Now we have to divide this by 2 because we have only one electron, right? If you're only adding, if you're adding 1 as a square and 1 as b square, then it would mean that A has one electron, that is, and that electron is occupying the 1 as a atomic orbital, and you took the square of that, then you get the electron density due to that electron, that is 1 as a square. And again, you suppose that B has another one electron, and it also has a density here, and that is the 1 as B square. Then you add both these two, then you get the total electron density here. So, but that is not the case here. We have only one electron. It means that we have to consider only that the first atom has half electron and the second atom has half electron. Okay, so that's a hypothetical case. So if you are considering only that the first and second atoms have half electrons each, and still they are not making the molecular orbital, then we have to consider, we have to divide this by 2 because both have half electrons. So the density will also be half. So this is the situation if there is no molecular orbital or question forming. So the size square or the probability in the midpoint, probability of finding the electron in the midpoint is 1 as a square plus 1 as b square divided by 2 if there is no molecular orbital formation. Okay, this is what we have to you have to consider if there is no bond, if there is no bonding, or if there is no molecular orbital formation. Okay, now we can consider what's the difference between these two. Okay, what's the difference between these two? And here we can see that here also 1 as A and 1 as B, and since it is the midpoint of A and B, 1 as A is equal to 1 as B here also, right? 1 as A is equal to 1 as B here. The same argument we can take there, because 1 as A and 1 as B has these expressions, right? These are the expressions for 1 as A and 1 as B, and then the midpoint both RA and RB will have the same value, therefore 1 as A will be equal to 1 as B. Therefore we can write it like 1 as A square, 1 as A square plus 1 as A square divided by 2, or 2 1 as A square divided by 2, that is equal to 1 as A square. Okay, that is the probability in the midpoint when there is no molecular orbital formation. And now we can examine what is the difference when there is a molecular orbital formation. Since there is a molecular orbital formation, the probability is 4n square 1 as A square. And if there is no molecular orbital formation, then the corresponding probability is 1 as A square. So what's the difference between both? The difference is 4n square, actually it is n plus square, 1 as A square, minus 1 as A square, right? As A square. So that is equal to 4 n square, n plus square minus 1 into 1 as A square. Okay, so that is equal to 4n plus square minus 1 into 1 as A square. That's a difference in the electron density when there is a molecular orbital formation. So, and this difference actually is as a positive difference. Okay, it means that when the molecular orbital is being formed, then there is an increase in the electron density in the midpoint. Okay, it means that between A and B, there will be an increase in the electron density that we would actually expect if there is no molecular orbital formation. അല്ലേ? ഇപ്പോൾ molecular orbital formation നടന്നില്ലായിരുന്നുവെങ്കിൽ നമ്മൾ എക്സ്പെക്ട് ചെയ്യുന്നത് വെറും 1 as A square ആയിരുന്നു. പക്ഷേ അതിനേക്കാൾ കൂടുതലാണ് ഇപ്പോഴത്തെ 4n square into 1 as A square എന്ന് പറയുന്നത്. അതായത് in between the nucleus there is a build up of the electron density. അല്ലേ? So in between the nucleus there is a build up of the electron density. So nuclei A and B, and in between the nuclei there is a buildup of the electron density. So what is the consequence of this buildup? Actually there is a repulsion between A and B, and this repulsion between A and B will push the two nuclei apart so that the system should go unstable or system should dissociate, right? But why it is not happening? This is not happening because the electron density is accumulating here, or electron density is being built up between the A and B. So there will be an attractive force between this electron density and nucleus A, and there will be attractive force between this electron and nucleus B. So not only the repulsive potential energy is working here, but also the attractive potential energy is also working. When nucleus A and nucleus B is repelling each other at the same time, there is an attractive factor there. Means the electron in between A and B are pulling A and B together, right? Okay. So that is the reason for the bonding. അപ്പോൾ ഇതുകൊണ്ടാണ് ഈ സിസ്റ്റം സ്റ്റേബിൾ ആയിരിക്കുന്നത്. അപ്പം ഇതെന്ന് പറയുന്ന ഒരു ബോണ്ടിങ് സിറ്റുവേഷൻ ആണ്, അല്ലേ? So if the electron is occupying the side plus orbital, then it will lead to the electron accumulation between the nuclei, and this leads to a stable system. Okay, now we can examine what is happening if the electron is occupying psi minus. What is happening if the electron is occupying psi minus? What is psi minus? 1 divided by root of 2 into 1 minus s, okay, into 1 as A minus 1 as B, and we can take psi minus square, that is equal to 1 divided by 2 into 1 minus s into 1 as A square plus 1 as B square minus 2 1 as A 1 as B, and in between A and B, okay, the midpoint in the between A and B, then psi minus square is equal to 1 divided by 2 into 1 minus s into 1 as A square plus 1 as A square. I put 1 as A square here because in the midpoint 1 as A is equal to 1 as B minus 2 1 as A. Okay, again I put 1s in place of 1s b. That means that 1 divided by 2 into 1 minus s into 1s a square plus 1s a square, that is equal to 1s a square minus 2 1s a into 1s b, that is equal to 1s a square. Okay, 2 1s a square minus 2 1s a square, that is equal to 0, that is equal to psi minus square is equal to 0. It means that if the electron is occupying the psi minus orbital, then if you are considering the electron density in between the nuclei, then the electron density is 0. What does it mean? If the electron is occupying the psi minus orbital in between the nucleus, the electron density is diminishing. Okay, if we are considering that if there is no molecular orbital formation, okay, ആ കേസിലായിരുന്നുണ്ടെങ്കിൽ at least there would be an electron density corresponding to 1s a square. But now, if the electron is occupying the psi minus orbital, then that is even less than 1s a square. It diminishes to 0. So we have two probability situations here, depending on where the electron is occupying. Where the electron is occupying the psi plus or psi minus. Well, we can plot psi plus and psi minus and psi plus square and psi minus square here. So let me plot psi plus. Okay, psi plus. So here is the nucleus A, and here is the nucleus B, and if I am plotting psi plus, the psi plus plot is actually like this. Okay, this is the plot of psi plus. Okay, and if I am plotting psi plus square, then the psi plus square plot is like this. Okay, and here you can see that in between the nuclei there is a considerable electron density, and this considerable electron density in between the nuclei is leading to bonding. Okay, so this is psi plus, and this is psi plus square. And if you are considering uh, sorry if you are considering the psi minus and psi minus square, here is the nucleus A and here is the nucleus B. So if you are considering psi minus, the plot of psi minus is like this. Okay, it will be like this. It will be like this. Like this, psi minus square. So psi minus. So this is psi minus, and if you are taking psi minus square, then psi minus square will be like this. Okay, and at that point it will be like this. Why it is like this? Because here it is minus. Okay, here it is minus, and the square of the minus will be positive. So that is why the psi minus square is like this. So this is psi minus square. So if you are looking at this psi minus square's plot, we can see that in between the nuclei, the psi minus square is actually diminishing to 0. It means that between the nuclei, the electron density is vanishing, and so this leads to an unstable system. So if the electron is occupying the psi plus, then it leads to bonding. So psi plus is called bonding molecular orbital, and if the electron is occupying psi minus, then it leads to an unstable system. That therefore it is called anti-bonding molecular orbital. Okay, so these are the physical meaning of psi plus and psi minus. So electron can occupy either bonding molecular orbital, or it can occupy the anti-bonding molecular orbital. If the system is in the ground state, then the electron will occupy psi plus, and there will be a bonding. Okay, the system's energy will be less than the energy of the individual hydrogen atoms, and if the electron is occupying psi minus, then the system's energy will be greater than the energy of the individual hydrogen atom, or you can consider like the energy of the individual hydrogen atom and the hydrogen ion. Okay, so you have two molecular orbitals, psi plus and psi minus. Okay, and if you are giving too much energy, then the electron can jump to the psi minus. If it is jumping to the psi minus, then the dissociation will definitely take place, and the system will go dissociated. The system will go unstable. So here we have a theory. What would we do? We actually derived the molecular orbital expressions based on the linear combination molecular orbital approach. Okay, then we got the expressions for the molecular orbitals, and we found that when the electrons are occupying the bonding molecular orbital, there is a conserved electron density build up between the nuclei, which is leading to the nucleus which leads to the stable arrangement of the two nuclei. Otherwise, the nuclei should repel each other. But since the electron density is being built up between the nuclei, it leads to a stable arrangement. Okay, that corresponds to bonding. So molecular orbital theory, that's a success. But still you have to remember that these values what we have obtained here, like 1.32 angstrom, are still far from the truth. So the theory should be refined, or the trial functions that we are taking should be refined. Okay, so there is a lot of scope for improvement. Still, we have a reliable theory to explain the bonding in the in systems having more than one nuclei. Okay, so I hope you understood this portion. If you have any doubt, you can contact me. Okay, thank you for watching, and bye.